All right, so I hope you can see this now.
Yes, we can see.
Yeah, okay, good. Okay, yes. So my talk here, just slightly modify 2 words. So conjugate connection and statistical mirror symmetry. First, I'd like to acknowledge my collaborators for this work over the years. So let's see. The plan of today's talk is that there are 3 parts. One is that I will give a basic introduction to the essence of the information geometry, namely the conjugate connection, the notion of the conjugate connections. And I'll give some motivations from statistics as to how this mathematical structure arises. So I will be talking about both the statistical structure, the standard information geometry structure, as well as the so-called partially flat structure, which my colleagues and I will have worked on in the past. And then I'm going to talk about how the conjugate connection would interact with a compatible triple on the manifold. So in particular, we are going to focus on transformation of the connections via or through this compatible triple, and how the statistical structure can be extended or enlarged to Hermitian structures and Kähler structures. And finally, we talk about the construction of statistical mirror symmetry. And this is something which comes out very naturally for any parametric statistical models. So we'll explain its construction and use the example of the univariate normal distribution. All right, so let me first start with the conjugate connections on the Riemannian manifold. So we are given with the Riemannian manifold and an arbitrary affine connection that may carry curvature or torsion. So we define the conjugate connection with respect to this Riemannian metric as follows. So basically, you have the given connection operates on the vector fields X, and the conjugate connection, well, another thing that operates on the other vector fields so that the G, the inner product, is preserved. Well, it needs to be proven that this is indeed an affine connection, and this can be done. In other words, you can verify the axioms for the affine connection and show that this is indeed an affine connection as well. And with this, we can also show that actually this operation of conjugation by G is involutive. So if you apply twice, it becomes the original connection. So we can then write this above equation and change the slots of its application. And this can all be verified. And that's our starting point. In other words, we are given with the nabla, and then we have a G, and the G, using the G, we define a conjugate connection, which is another connection on the same manifold. Now, this nabla and nabla star, the 2 connections operates on the sections of the tangent bundle, okay? So they operate on the vector fields. The average of that is parallel with respect to the metric. It may carry torsion though. So having defined the idea or the notion of the conjugate connection, let us also define another notion, which is called the Kudazi coupling between G and nabla. So the Kudazi coupling of the G and nabla is basically that nabla G is symmetric. So the covariant derivative of G is symmetric with respect to, so here you can see that's a definition. So the covariant derivative is, of course, defined in the usual way. So we have defined the conjugate connection, and we have defined a Kudazi coupling of the nabla and G. Now, we can show very readily that these 2 conjugate connections, they satisfy this equation with respect to the Riemannian curvature tensor. this says that the conjugate connections, they must be curvature-free jointly. In other words, if one is curvature-free, the other is also curvature-free. Now, with respect to torsion, it turns out that you also have an identity. The identity is that the left-hand side okay, sorry, I just there's a disconnect on my side, I guess. Let's see. Let me just re-pull this up. Sorry about that. Okay. 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 So I have to reshare my screen here. Just a second. Okay, sorry about that. So let's see, coming back again. So with respect to the torsion, then, so we just talk about for curvature, they are jointly curvature free, but with respect to torsion, so the difference on the left-hand side is equal to the difference of the torsion tensors between nabla and nabla star. So the notion of the Kudazi coupling, that is to say, if nabla G is symmetric, right? That's the definition of the Kudazi coupling. When nabla G is symmetric, then the left-hand side would vanish, which means that the torsion of nabla and nabla star would be the same. So we can say that the torsion of the conjugate connections, they are preserved under this conjugation. So the torsion is preserved under this conjugation by the G. And curvatures, they would vanish jointly. And this is very important for us when we construct the statistical mirror symmetry. Now, let us then recall some standard definition of the statistical structure. So there are several equivalent definitions of statistical structure. So Amari first came up with this structure where you have a Riemannian manifold and a pair of conjugate connections, and that they are both torsion-free. So that's the definition of a statistical structure or a manifold, a statistical manifold. This definition can be equivalently stated in the case of Lorentz. Just basically, on the manifold, you have a Riemannian metric and a symmetric 0,3 tensor. So a Riemannian metric with a symmetric 0,3 tensor field, you can show by this symmetric 0,3 tensor field, you can construct this K, which is a 1,2 tensor field, and then construct a pair of conjugate torsion-free connections. So that's another equivalent way of defining a statistical structure. And thirdly, we have a Riemannian manifold and given a connection such that the covariant derivative of the connection with respect to the metric would be symmetric. So these are all three equivalent ways of defining this so-called statistical structure. And this is the data we have when we carry out the subsequent discussions. I'll mention that this is actually the standard definition for the statistical structure or the S structure. And we are going to talk about some other an extension or generalization of this kind of conjugate connections. But let me first explain why this structure, the statistical structure, is an important object to study for applied mathematics, in particular in statistics, machine learning, information theory, etc. This is because we start with the so-called contrast function. So a contrast function on a manifold is a two-point function. This two-point function is non-negative and smooth, that is differentiable up to second order. So given this contrast function and working in any local coordinate charts, we have the following expression. We have the following requirement indeed. That is, so it's non-negative, it's 0 if and only if x is equal to y. And it is smooth. The first derivative vanishes as x equal y at the diagonal. And the second mixed derivative, if minus of that, is the positive semi-definite. So here the subscript d sub I is the partial derivative with respect to the xi, and the comma I is the partial derivative with respect to the yi. So we have these notations. It turns out that in 98-92, a Japanese statistician, Eguchi, showed that any contrast function would induce a statistical structure along the diagonal of M cross M. So I'm going to explain this method, the Eguchi's method for inducing the statistical structure from the contrast function. So contrast function, basically, when you expand it, when you do Taylor expansion, the first order would vanish because of its definition. So the only first surviving term is the second order. The second order, if you do the mixed derivative of xi and yj, which can be shown, readily seen, is actually symmetric with respect to yi and xj. And this is a symmetric and by assumption, positive semi-definite matrix here. Now, if we look at the third order, namely, we perform derivative with respect to x twice, xi, xj, and then do yk and set them y equal x, that we call it this gamma. We perform yi, yk, and then x, yi, yj, and xk, we call it gamma star. It turns out that these quantities which are derived would satisfy this equation. And this is the equation which is the expression of the conjugate connection in local coordinates. So therefore, from any contrast function, we can perform this procedure and derive what will be a Riemannian metric and what will be a pair of torsion-free affine connection. Now, torsion freeness is because of, you look at this subscript ij, and we perform the partial xi, xj, so it is obviously symmetric. So it's torsion-free. So both gamma and gamma star are torsion-free. Now, this construction is very useful for the study of statistics. For statistics, let us consider a parametric probability density, a family of probability density functions indexed by some parameter theta. So random variable here is indexed by omega, and the parameter theta index the particular probability function. And theta then can serve as a coordinate chart and then form this manifold M sub theta. So each point on this manifold is just a probability density function. And turns out that César, he was information theorists in 1967, he defined a class of function called F divergence or F contrast function. Divergence and contrast are synonymously used in this community. So it's F divergence. So F divergence measures the directed difference or the directed distance between two probability density functions indexed by theta prime and theta. And this F function, you can show that it defined is a proper divergence function or contrast function. And once we perform the Eguchi's method on this divergence function, here I use the L to denote the log of P, Then you can immediately derive that the Gij, the G, is of this form. Is the expectation of the so-called score function in statistics. So this is a well-known Fisher information. It's a Fisher information, which is the most well-known quantity in statistics. So since this Fisher information is used as a Riemannian metric, this metric is called the Fisher-Rao metric. And the fact that Fisher-Rao metric is the lowest order approximation for the so-called Kullback-Leibler divergence, which is a very special case of this F divergence. And this is known to statisticians in 1950s. So this structure arises very naturally from statistics. Now, if we perform the Eguchi's method to obtain a pair of conjugate connections, gamma star and gamma, and then we take the difference of them, this is the 0,3 tensor we obtain, Cijk. This quantity is also an important statistical quantity. Chenzov in 1972 showed that G and C are unique second and third order invariants under the Markov morphism, that is relabeling of the random variables. And then Amari in 1980s first obtained this kind of a dualistic geometry, the gamma and gamma star. Well, here gamma now is just the coordinate representation of nabla. So the dualistic geometry was obtained by Amari, and then Lauritsen further clarifies that the C tensor here is just gamma star minus gamma. So statistical structure basically is the data on the manifold, which is given by parametric probability models. So it is the Riemannian structure along with this conjugate connections that underlies all statistical models. So this is the data G nabla nabla star, or GC or G nabla, where nabla G is symmetric. This is three different ways of representing the same geometric data on M that we start with. So what is information geometry? Information geometry, if we very narrowly speaking, this is the differential geometric study of the manifold of this probability, parametric probability distributions or probability density functions with the following given data, that is the G and a pair of conjugate connections, and L is the log likelihood function of the probability model. So you can see, given any probability model, a parametric probability model, we can induce these geometric quantities. So that's the narrow definition of information geometry. Now, broadly speaking, information geometry can be defined as a geometric study of this kind of this dualistic structure of a manifold that relates to the conjugate connection. So the essence of this is the conjugate connection. Now, in recent years, people are extending the statistical structure while still keeping or looking at this conjugate connections. So Kuruse, a Japanese geometer, defined the following structure. So manifold M, G, and nabla. Now, instead of assuming nabla G to be quasi-coupled, that is nabla G is symmetric, he defines this case when nabla, the torsion of nabla is equal this difference in symmetry of this left-hand side. So when nabla G is symmetric, the left-hand side is 0, so torsion is 0. So you can think about quasi-coupling as a special case where a connection is torsion-free, right? So this would be a more, well, it's not a generalization, but it's an alternative a way of coupling nabla and G. This is called a torsion coupling. Torsion coupling. If nabla is torsion coupled to G by this definition, you can show very easily. You can see actually that the conjugate connection is torsion free. Okay, so these are the. So in this case, we would also have a pair of connections, and this pair of connections have the following property that one of them is torsion free and one of them carries torsion. Now, if we further assume that this connection nabla is curvature free, this is called the partially flat manifold. Partially flat in the sense that the nabla, the connection is free, is curvature free, but may carry torsion, but nabla star is curvature free because they are curvature free jointly, and then it carries, it does not carry torsion. So this is a flat connection. So this is called a partially flat manifold. So this is an alternative model for the parametric probability family, and also with the conjugate connection. In this case, in the partially flat model, essentially the parameter theta is being treated as an affine coordinate chart. And when we take the Fisher-Rao metric G, then it forms in generally a partially flat manifold. So let's give an example for the probability family. So this is the familiar example of the univariate Gaussian distribution on the real line R. So we have this where omega is a random variable taken on the real line, and mu and sigma are the parameters. So for this parametric family, the parameters mu range through R, and the sigma range through the non-negative number, real number. So when sigma go to 0, this is essentially the distributions, the delta distribution. And when sigma go to infinity, it's a uniform distribution. These are non-proper densities. They are linear functional on test functions, but they are the limiting case for this family. So if we geometrically present that, so we represent mu as the real line here, and we have an XY plane. The upper half plane indeed is a representation of the family of normal distributions. Sigma can take from 0 to infinity. So all the points along this line are these delta functions, in non-proper density function, and the point at infinity is also the uniform distribution, also a non-proper density function. So each point represents a normal distribution, which is on the right-hand side. So the univariate Gaussian distribution or normal distribution is, so 4 normal distribution mapped to 4 points here. So while from statistical consideration, it is obvious that these two distributions are actually farther apart because they have smaller variance. These two, which are closer, they have larger variance. Okay, given that the separation of the mean is the same, so that's from statistical. Statistical meaning is very clear. With respect to this family, the Fisher-Rao metric, we can derive it, which is has this very simple form, and in fact, this is if we actually calculate its Riemann curvature tensor for the Levi-Civita connection, it is constant negative curvature. It's a constant negative, the curvature has a constant negative value. So it's the hyperbolic space of the upper half plane. But this metric is not a Hessian metric, and we'll explain more later. So if we actually calculate the Levi-Civita connection, so this is the Levi-Civita connection expressed as Christoph symbol of second kind. Okay, so the Levi-Civita connection has constant negative curvature, but interestingly, when we calculate the conjugate connections, turns out that they are curvature free. So in fact, on this hyperbolic space, we can prescribe a family of connections, alpha. Alpha is a real number. So we have a family of alpha connections in which zero connection is the Levi-Civita connection, and the alpha connection and minus alpha connection are conjugate to each other. And this gamma and gamma star is just 1 and minus 1. And this pair turns out to be both, they are both curvature free, and of course they are also torsion free. So they're both flat, they're dually flat. So they form what is known as the Hermitian manifold, the Hermitian manifold. So because of that, we know then there need to exist the affine coordinate system on this manifold as well, even though mu sigma is not an affine coordinate system, because the metric expressed in mu and sigma are not Hermitian metric. So but we can find the Hermitian metric, okay? So if we look into the finding the affine coordinates, the Hermitian metric and its meaning, we realize that normal distribution, originally it was a so-called a location scale family. Location scale family because it has centered on mu and it has a variance of sigma, it's a location and scale. Turns out that this normal distribution with location and scale variables mu and sigma, we can also write it as in this form after we do some manipulation. Now, this F1, F2 are the given functions, random functions, these are random variables, and X1, X2 are the new parameters as a function of the old parameter mu and sigma, okay? So mu, X1, X2 can be written just as a transformation of the mu sigma in this way. This form is known to statisticians as the exponential family, So the exponential family, and this, with exponential family, and then we also, if we perform the expectation on these random variables on this F1, F2, which are called the sufficient statistics in the exponential family, what we find is that U1, U2 are also given by this mu and mu and sigma. So they are also the functions of mu and sigma. So we have the U1 and U2. And U and U2 are also related to X1, X2 in this way. And this, if we calculate the Legendre dual of this phi is a generating function for the exponential family, right? Phi is like this. Phi is here. It's a normalizing function. This function makes this exponential family normalize to 1, which is this, has this form here. This is the phi. And if we take its Legendre conjugate, turns out to be nothing but entropy, the Shannon entropy function. Okay, so from this analysis, you can see that all these properties are embodied in the geometric structure, because from geometric structure, we first derive that there is the Hermitian manifold. There is the dually flat structure. The affine connection have a dually flat. So we go about and trying to find these affine coordinates, and the affine coordinates turns out to be X1, X2, and U and U2, which are transformations of the mu and sigma. And these convex potentials have meanings in information theory, in statistics. They are the Shannon entropy. So that gives us some encouragement as to why we want to actually study this geometry. So when we write the Hermitian, when we write the Fisher-Rao metric in these coordinates X1, X2, we actually indeed get a Hermitian metric using the phi, and we will write that in U. Then we also get the Hermitian metric. So we have two. Well, this is one and the same, because if you do a coordinate transformation, this is the same. In fact, the Riemannian metric is the same, but the fact that it can be written as a Hermitian on this with respect to these special affine coordinates, and this is something that can come out very naturally from a geometric analysis. Now, I'm going to now talk about this notion of the conjugate connection and then compatible triple and how they interact with a compatible triple. So, so far in the standard information geometry, we studied the G conjugate with respect to the Riemannian metric. Over the years, my colleagues and I, we studied other notions of conjugation, in particular, the conjugation with respect to non-degenerate two form. Okay, so in this case, we can also define the conjugation in the same way as for G. Of course, we need to verify this is indeed an FN connection and has the same property that it is involutive. So it can be defined, well defined for each of the slot. Now, this is joint work with Fei Ten. So we can show that actually in this case, now the so-called Kutazi coupling, this Kutazi coupling, because of omega is a skew symmetric, Kutazi coupling is the same as saying that the nabla and its conjugate connection, nabla-dagger, are the same, which then imply that the torsion of nabla and nabla-dagger are the same. So nabla and its omega conjugate are the same if and only if their torsion would be equal. Now, let us also look at the situation where, well, here we assume the dimension for the manifold is even dimensional. So we look at the endomorphism of the tangent bundle and the section that and the map that it induced on its section. Okay, so this we denote this L. L is also known as the gauge transformation. Okay, so we apply this gauge transformation to the nabla, which is defined in this way, to obtain the nabla L. So nabla L, given the nabla and given an L, and we can define this, which can be shown to be an FN connection, the gauge transform of an FN connection. Now, this set of invertible operators, or the L's, the set of invertible L's on here, they will form a gauge transformation group, and with the group operation defined in this way. So it is easily shown that the average of these would be parallel with respect to L. Okay. So we can also define the Kutazi coupling of L with respect to nabla. And it is known that this nabla and L, if it's Kutazi coupled, then nabla L inverse is also Kutazi coupled, which is the same as the torsion being equal. Okay. So I need to hurry a little bit because I'm but we are going to look at a special case where L square is plus minus identity. So in this case, we are looking at the almost complex structure, J square equal minus identity, or para-complex structure, K square equal plus identity. And we look at its compatibility with respect to the Riemannian metric. J is, in this case, a standard almost complex structure compatible with the Riemannian metric G. And here, it's had to be pseudo-Riemannian metric because it need to have split curvature. But in both of these cases, we can have the compatibility. We can write out the compatibility condition, and also we can construct a skew symmetric two form. And we form a compatible triple. We form a compatible triple in this case. So now, with respect to for a given connection, with respect to G, we have the G conjugate. With respect to omega, there's omega conjugate. With respect to L, we have the L gauge transform. And in this case, when they form a compatible triple, we show that if they form a compatible triple, then these transformations, these three transformations, conjugate transformations, along with the identity operator, would form a four-element Klein group. In other words, they are involutive, and the composition of them gets to the third. any two composition gets to the third. Okay, so you have this very nice structure of the transformation of the connection for any connection. So here nabla can be any connection. We didn't restrict it to any quasi-coupling or torsion freeness and so forth. So this structure is of great interest to us. And it turns out that, yeah, I want to mention a little bit about this, a cousin of this structure with the anti-Hermitian or the northern structure, which is, I think, very familiar to many people in this audience. So, so we looked at the we have looked at the para-Hermitian structure K, in this case, with the split curvature, with the split signature of G and a skew symmetric omega. But we can also have the so-called anti-Hermitian structure, which is different than the para-Hermitian structure. It's also have a split signature on G, but it has a twin or associated metric. It's a symmetric form as opposed to skew symmetric form here. So it turns out that these conjugate connection on the northern manifolds has also has been studied. And turns out also they would obey this kind of Klein transformation group as shown by Professor Giza and his colleague. So this proof was following the proof that we gave for the case of the Hermitian and para-Hermitian case. So a lot of these structures can be extended or can have their analog in the northern manifold situation. And this is something that can be
There is a little internet connection problem. We are waiting for Professor. Dear participants, we have a little problem about the internet connection of the Professor Zhang, and we are waiting their connection until he came. We give a little break. Please follow the timer in the screen.
Well, sorry, just
Okay, no problem, Professor. It's possible when we are making a webinar.
yes. So this is okay. Am I still getting here? Let's see. Okay, let me just put this on again.
Don't be hurry, take
All
your
right.
time.
Okay. Yes. Okay. So yeah, I don't know what happened with the network. This here is just maybe it's because of the snow. We had a big snowstorm right now.
Maybe
So
it's
this
possible.
is kind of, I don't know what's the situation. Okay. Oops. Okay. So
Okay, we are waiting.
yeah. Okay. Yes. Okay. Sorry. Yeah. So okay. I think I will try to skip a few things. So basically, we can. Yes, we can derive the interaction of the nabla with the compatible triple, and then in particular, I want to mention one thing is that we investigated the case where how an integrable structure of L, how the integrability of L can be linked with the torsion of the nabla on the manifold. So this is some, we derive some conditions, what we call the torsion matching condition of nabla with L. And we show that this actually extends the canonical connection, the first canonical and second canonical connection along the Kudashian line of connections. So this is a generalization of their notions. And we also showed that on an almost Hermitian manifold or almost para-Hermitian manifold, given any nabla, of course, we have the quadruple of connections, the G conjugate, the L conjugate, the omega conjugate. And turns out that if any of the four is quasi-coupled to G, and if any of the four is torsion coupled to G to L, then all of them have to be quasi-coupled to G, and all of them will be torsion coupled to L. And the average of this is the Chen connection. The average of nabla with nabla L, the average of these, they are the Chen connection in the sense that, so they are parallel with respect to G, omega, and L. So we can generalize the standard, structures that's studied in complex geometry, and we have also looked at the case of the Kähler manifold, in which case then the nabla would be torsion-free, and we define the so-called quasi-Kähler structure, and then we show that for a statistical manifold, if there is a almost complex structure, almost para-complex structure that's compatible with G and is quasi-coupled to nabla, then it is a Kähler manifold or para-Kähler structure. Okay, so this is again saying that for if we given a torsion-free nabla and its transformation nabla star, nabla dagger, nabla L for any compatible triple L,